Solar geoengineering is the possibility of deliberately making the Earth more reflective by engineering means to reduce some of the risks of accumulated greenhouse gases which are causing climate change. There are all sorts of potential risks and downsides to solar geoengineering, and we want to tell you about some new work we've done that we think reduces some of the technical risks in a way that really is exciting and points to what could happen if there's a larger research effort on this topic. So the way that we're most confident that we could make the planet more reflective is to put sulfuric acid aerosols into the stratosphere. What are the technical risks of sulfuric acid as a way to make the planet more reflective? I'm not thinking here about the ways in which making the planet more reflective does not, of course, perfectly compensate for all the damages caused by increasing CO2. That's a very important topic, but not what we're dealing with here. Here our topic is, if we ever wanted to actually do solar geoengineering to increase the reflectivity of the Earth, what are the ways we could do it and how could we reduce the risks? There are two well understood technical risks to using sulfate aerosols as a way to make the planet more reflective. One is that sulfates can further damage the ozone layer, and two is that they heat the lower stratosphere, changing stratospheric circulation. So, how could we reduce these two risks? We've looked at the possibility of adding solid aerosols to the stratosphere instead of liquid sulfate droplets. In this new paper, we went a step further, thinking maybe there's a way we could use aerosols which are actually chemically reactive. And the idea is in some ways completely simple. The idea is add a base, a common base, like calcium carbonate, the same chemical as is in limestone, to the stratosphere, where that base will react with many of the acids that are active in destroying ozone. Hydrochloric acid and nitric acid being among the most important, as well as the existing sulfuric acid. All those acids will react with calcium carbonate to make common salts, which would then rain out into the lower atmosphere. So we've tried this out in a state-of-the-art chemical model, and it looks like we could both increase the reflectivity of the Earth, cooling the planet by a degree or two, and also restoring the ozone layer. That's amazing in the sense that we might reduce part of the climate risk, and instead of increasing the ozone layer risk, we'd actually help to heal the ozone layer. And at the same time, by really pure luck, one of those fun lucky breaks in science, it turns out that calcium carbonate is actually a better stratospheric scatterer than sulfuric acid because it absorbs less light, and so it does less of a job of heating the lower stratosphere, which is something we'd like to avoid. The idea is easy, but building a quantitative model to see how it might play out in the real world was pretty hard. This work started about 4 years ago when Deborah Weisenstein, working with me, began to develop a model that would treat solid particles in the stratosphere in a more physically realistic way. And now we're able to use that model to investigate how the stratosphere might react to adding new chemicals like calcium carbonate.
The Keys Group has been working on geoengineering for quite a while, and we've done a lot of modeling of sulfate aerosols and how they could be used for geoengineering. And we've been searching for a different kind of particle that could minimize some of those side effects of geoengineering so that you can get the reflectivity without these other adverse impacts. The bottom line in some of this research is that we were able to compare various geoengineering methods with potential changes in ozone from those same methods. And the figure shows the amount of geoengineering we can achieve versus the amount of ozone depletion that comes from the same technique. With sulfate geoengineering, we've always found there was quite a bit of ozone loss. With alumina geoengineering using these solid particles in the stratosphere, we can achieve quite a bit less ozone loss for the same radiative forcing. And with calcite, we've seen that we can achieve the same radiative forcing without those detrimental effects on ozone, perhaps even slightly increasing the ozone column.
The basic idea, pun intended because it's a base, is simple enough, and part of it probably is robust. But the specific chemical reactions are deeply uncertain. To reduce that uncertainty, we need to do laboratory experiments to understand in more detail how reactions with stratospheric chemicals on the surface of these calcium carbonate particles would work. And in the end, we'll need to do field experiments where we release small amounts of calcium carbonate, less than you could hold in your hand, releasing it into a cloud, a small cloud in the stratosphere, where we could directly measure the effectiveness of these particles in reducing ozone loss.
The main aspect of the paper that is really groundbreaking new is that by using a highly reactive aerosol, we can have control of, for example, stratospheric ozone. Previous work always used one type of aerosol, for example, sulfate aerosol. And that means that the negative impacts that are tied to sulfate aerosol, such as the heating of the stratosphere and ozone destruction, are directly correlated with a positive impact we're interested in, which is the scattering of sunlight back to space. By introducing a new type of aerosol, you're decoupling the scattering back of sunlight to the stratosphere from the ozone destruction and the stratospheric heating, and hence you now have the possibility to have potentially two different knobs, one for the sort of radiative forcing solar sunlight being scattered back, and the other knob for controlling ozone destruction and stratospheric heating. And so, of course, one of the most compelling ideas to me is to go beyond this and say, well, what about thinking about combining different types of particles which allow you to give different control of these knobs and perhaps additional knobs? Because, of course, the idea that one type of aerosol injected in one particular way is the best possible solution seems extremely unlikely and even naive.
To advance solar geoengineering to the point where meaningful decisions about implementation could be made, perhaps a decade or two in the future, requires work across a multitude of disciplines, from science and engineering to the social sciences to hard questions that every citizen has a voice in about how on earth we should govern the planet at this scale. And that requires a broad collaborative effort, the kind of effort we're trying to build at Harvard and trying to foster elsewhere in the world.